So for the first one, what we have is y prime, or dy dx, is equal to e to the sine x multiplied by cosine x. And you can put the cosine x first if you like. That's totally fine. In order here, because it's multiplication, does not matter. To do the second one, we are going to be using the natural log derivative. So the derivative of the natural log is 1 over whatever that is times the derivative of that. So dy dx is going to be equal to 1 over x squared plus cosine x. So this is going to be multiplied by the derivative, which is 2x negative sine x. And of course you can put 1 over the other as well. So you can write it as 2x minus sine x over x squared plus cosine x. And then on the last one, what'd you all get for the last one? You ready for this? The last one's just 2x. So dy dx. The last one's just 2x. And the reason the last one is just 2x is because we have this rule when we're talking about exponents. If we have b raised to the log based b of x, this just equals x all day long. So e raised to the natural log of x squared is just x squared. So I can just do the derivative of x squared. Now the reason I did that one is because if we don't have ideally we have all of our laws of logs memorized, and I know that's not necessarily true, but if we're asked to do y is equal to 2 to the x, and we're asked to do the derivative of that, then we can use this and this combined to make it so that we can do the actual derivative of it. So if I'm asked to do that, then I'm going to rewrite this as e raised to the natural log of 2x, because I'm using this rule right here in reverse. And then I'm going to use another rule that says if I have an exponent, I can bring that down on front. So this is e raised to the x natural log of 2. Now I'm going to do my derivative the way I normally do my derivative. So dy dx is going to be e x, the natural log of 2, multiplied by the derivative of that, which is just going to be the natural log of 2, because the derivative of x is just its constant. The natural log of 2 is a constant, but this part right here gets replaced with what we started out with. So this is going to just be 2 to the x multiplied by the natural log of 2. So when we see that pattern, when we see 2 to the x, the natural log of 2, or 3 to the x, the natural log of 2 as the derivative, that means when I do the antiderivative of it, it must have been 2 to the x is what I started out with. Is there any questions on that? Any of those? All right. So if there's no questions, then we're going to go back over here and we're going to say, okay, here's some more integrals that I'm going to need to know and write down. If I have e to the x dx, this is e to the x all day long, so we like that. If I have a raised to the x, if I'm doing the integral of a raised to the x, then I must have started out with a to the x, some a being some base, not 1 or a negative, over the natural log of a plus c. Now remember that if I have something that looks like this, I have d du of e to the u. That means I must have e to the u prime. The reason I'm reminding you of that is because when I take a look at a, if I were to have done the derivative of e to the 2x, what am I missing there in my integral? What am I missing? What do I need to adjust for? If I were to have done the derivative of e to the 2x, what should I have had there that is not there now? What am I missing? Well, if I were asked to do du of e to the 2x. What should this be if I do the derivative of that? Using the rule right here, what should I have gotten? I'm missing a 2, right? Because I would have had e to the 2x, the derivative of 2x is just 2. I am missing a 2 right here. So how do I adjust for that when I do the antiderivative? Yeah, I've got to have that adjustment. I have to put 1/2 in front when I do the antiderivative. So I know that this is going to be equal to 1/2 e to the 2x plus c. Now when I do the derivative of that, that 1/2 as a multiplier is going to cancel out that 2, so I will get just, when I do the derivative of that, I will just get e to the 2x. And if I'm not certain, then I can always do the U substitution. I would have said, let u equal 2 to the x. That means du is equal to 2 du. And I can see I have the dx, or that should be dx, so 2 dx. I see I have the dx, but I don't have the 2 there. So what I would have done is to made the adjustment by saying 1/2 du is going to be replacing dx. So then this would have been, with U substitution, e to the u du with a 1/2 out front, because I am missing that. And so that would have been, by using the U substitution, 1/2 e to the u plus c. And then I just got to remember to replace my u back. So 1/2 e to the 2x plus c. So I can do it by U substitution. Or I can just say, hey, if I would have taken the derivative of e to the 2x, I should have had a 2 there, so I could have made the adjustment. So it depends on how you look at it. You can say, I need to use U substitution, totally fine. Or you can say, nope, I'm good. I just know I need to have that adjustment. So what I'd like you all to do now is I'd like you to do B, please. Answers are, I realize I need to adjust for the negative, first of all, and I need to adjust for the 3. So when I do the integration of e raised to the negative 3x dx, then I need to adjust for the negative 1/3 e to the negative 3x plus c. How was that so far? Okay, so I'm going to talk about D. I'm not going to do it, but I am going to do something similar to D. So if I were asked to integrate 4 raised to the negative 2x dx. Now, I have this up here. Do you see I have this rule? But for that rule, what's happening for that rule is I only have a base raised to an x. Because I have a base raised to just a simple x, I need to do some sort of adjustment. If I were asked to do the derivative d dx of 4 raised to the negative 2x, then this is going to be equal to d dx of e raised to the negative 2x, the natural log of 4. And I'm using the rule from over here, this rule from over here. So if I were to do the derivative of that, then that's going to be equal to e raised to the negative 2x, the natural log of 4, multiplied by, and the only variable I have is this x. The negative 2 and the 4 are just constants. And so I would have needed a negative 2, the natural log of 4. Now, this is the same thing as 4 raised to the negative 2x, I'm just replacing that back, minus 2, the natural log of 4. Now notice I have a negative 2 there. So if I have a negative 2 there, if I am asked to do the derivative here, and this is what I get to use, then I am missing a negative and a 2. So if I'm asked to do this derivative, this antiderivative, then it's going to be 4 raised to the negative 2x. And I'm missing the negative 2, the natural log of 4 plus c. I am missing this piece of it. So I have to adjust for it. So if I have something attached to my exponent, like a negative number, then the way I adjust for it when I integrate is I have that division right there. So on 2, straightforward, no work done. I just use this formula right up here. For C, I just do that. But for D, I have to adjust for that negative on that exponent of x. So go ahead and do C and D, please. Look at these. So using the straightforward, here's the definition of the integral of a raised to the x. On C, there's no adjustments I have to make because my exponent is a positive 1. So I can just write this as 2 to the x over the natural log of 2 plus c. So no worries on that one. However, on the second one, I do have to adjust for the fact I have a negative in there. So this is going to be 3 raised to the negative x divided by the negative, the natural log of 3 plus c. Or you can pull that negative out front. That's okay too. So what I mean by pulling the negative out front is I can just write this as a negative 3 raised to the negative x over the natural log of 3 plus c. How are we doing? How are we doing? Any questions so far for me before we continue? Anything at all? Okay, so if I were asked to do, so the question is, why do I have to deal with a negative? So let me erase all of this. If I were asked to find the derivative, and this is the great thing about and I was just waiting for my software. Today my software is just not playing well with me. My first class, it crashed a couple of times, which sucks ass to like no other. So if I were asked to do the derivative of this, then I know what the derivative, if I were asked to do dx of 3 to the negative x, I'm going to ignore that constant because it's just going to be 0. Then I know that this is going to be equal to 3 raised to the negative x. And then it's going to be, oh, for the love of gophers. Okay. And then I know it's going to be multiplied by the natural log of 3, and then it's going to be a negative out front of that. That's what I know it's going to be. So that is what the derivative should be. So if I was asked to do the derivative of 3 to the x, 3 raised to the negative x, then it's going to be 3 raised to the negative x multiplied by the negative natural log of 3. If I were asked to do this dividing by the natural log of 3, then the natural log of 3 is just a multiplier. So I would just put this multiplier there, and I would have ended up with a negative 3 raised to the negative x. That's would have been my derivative. I don't see a negative here. Because I don't see a negative here, I have to adjust for it somewhere. And the way I adjust for it is I say, okay, I know that if I were asked to do the derivative of 3 raised to the negative x, I better have gotten a negative. So when I do the antiderivative, I have to put a negative back on there because I should have had a negative 3 raised to the negative x, so I better adjust for that. Does that answer your question about why the negative was there in my final answer? Okay, cool. So what other kind of questions do you have for me? All right, here's some more rules. Look at this loveliness. Here are some more rules. We talked about this the last couple of days when we see x raised to the negative 1, in other words, 1 over x. It is always going to be the integration, or the antiderivative is going to be the natural log of the absolute value of x. When we see the natural log of x, which is awesome, we've now make sure that you pay attention to this one. This is something new. When we see the natural log of x dx, it is going to be equal to x, the natural log of x, minus x, plus our constant. So that is something new. We haven't seen that one before. And then, of course, we have this one as well, which is the log base a. So I'm not using base e. So any base, the common base, or base 2, x, the nat dx. I apologize. My son is power washing the house right outside my window. Because, you know, he doesn't know that I have class right now. Oh, wait, he does. And his cat was sitting in the window, so he's decided to scare his cat. So I get to hear this, and I apologize. I truly apologize. Life is so interesting in lockdown. This is the best. All right. So I want you to go ahead and see if you can do these. And you may have to do U substitution. So I want you to go ahead and try these. Go as far as you can with as many as you can. And you may have to do U substitution to get these to go. So I'm going to put this on pause and let you all try these. So as we take a look at B, when I'm using the rules, the power rules, and I have just a U or an X, to when I do the integration, if it isn't currently at a power of 1, I need to add 1 to it, and then I need to divide by that new power. So when I integrate, I'm undoing the derivative, which means when I'm doing the exponent rules for derivatives, I would have subtracted a power down to do the derivative. That means I need to add a power back. And when I'm doing the derivative, I take that power and use it as a multiplier. So when I do the antiderivative, I have to divide by that power after I've added 1 to it. And so that's why it's going to be divide by 2, and that's why it's going to be squared. And just keep asking the questions. I mean, keep asking the questions. I know myself that when I am following along in anything and I don't know, like a math question or something else, that science or whatever, if I don't know one step, it makes me hard to follow the rest of it. So please continue to ask the questions. Now on C, when we do the natural log, let u equal the natural log of x, then du is going to be 1 over x dx. So this part gets replaced with du, and this part gets replaced with u. And so this ends up being the integral of 1 over u squared du. And then this becomes the integral of u raised to the negative 2 du. The only reason I do that is because I want to be able to add that power and divide by it. So I'm going to add the power and divide by it. So when I do the integral of this, it's going to be negative u raised to the negative 1 plus c, which is equal to, this is going to be equal to negative the natural log of x raised to the negative 1 plus c, or if I prefer, negative 1 over the natural log of x plus c. How was that? Any questions at all on that? Anything at all on C? Let me pause it. Okay, so let me just take a moment to erase all of this so I can give myself some space to do D, if there's no questions. So when you're doing these and you see natural log anywhere, it's almost always going to be a U substitution. And then it's just a matter of choosing the best U substitution. And just like when we were doing the trig identities, sometimes it takes us more than one run at it. So if I let U equal the natural log of X, then du is going to be 1 over x dx. So this part gets replaced with du. So, and this part here gets replaced with u, and this part here gets replaced with u. So what I have now is I have the integral of 1 over u, the natural log of u, du. So I'm going to stop there and ask, let me rewrite this as the integral of 1 over x, the natural log of x, the natural log of the natural log of x, dx. When I did du is equal to the natural log of x, that means wherever I see the natural log of x, I replace that part with u. So those get replaced with u. And then when I did the derivative of the natural log of x, if I rewrite this as their integral of 1 over x multiplied by 1 over the natural log of x multiplied by 1 over the natural log of the natural log of x dx. Again, this place gets replaced with u. This gets replaced with u. And these two things here get replaced with du. Let's continue. Now, that kind of looks like, well, none of them. Well, that kind of sucks. But you know what? If I can do the U substitution once, guess what I get to do? I get to do the U substitution twice if I want to. So now what I'm going to do is say, okay, let V equal the natural log of U. So if V is equal to the natural log of U, then this is going to be dV is going to be equal 1 over U du. So that means this gets replaced with V, and this gets replaced with dV. And I'm going to stop. I'm going to ask you, what kind of questions do you have for me? All right, so then this is going to be equal to the integral of 1 over V dV. 1 over V dV. Now I can integrate this, and it will be a whole bunch of back substitutions, and it will be like the best thing we've ever done in our entire lives. Holy crap, this will be delicious. So now I can just do my integration, and this is going to be equal to the natural log of the absolute value of V plus C. But I'm not doing V, so I have to go backwards. So I'm going to go back, and wherever I see V, I'm going to replace it with the natural log of U. So this is equal to the natural log of the absolute value of the natural log of U plus C. But wait for it, we are not doing U, we are doing X. So this is equal to the natural log of the absolute value of the natural log of the absolute value of the natural log of X. And there's my final answer in all of its glory. Aren't you glad you showed up today? Look what you get to do. Pretty much the natural log of the absolute value of x. Oh, I need to put my absolute value in the right place. It needs to go right there. Woo! Good times. Good times. And I chose this example not to make your lives miserable. I chose this example because this is like the worst of the worst, and you have to do U substitution twice. It is not uncommon to have to use U substitution twice or even 3 times. So it's okay to do it more than once. If you don't get what you need the first step, you may have to think about it a secondary U substitution. How was that? All right. Now, if there's no questions on that, I'm just going to wait. If there is no questions on that, then as a hint for E, you're going to rewrite it using the using how tangent is defined in terms of sine and cosine. So this is the integral of the sine of theta over the cosine of theta d theta. So since we don't have an integral for tangent, we go into the sine over cosine, and then I do U substitution. I use U substitution here. So if there's no questions on D, then I'm just going to scroll down and go in bigger so you can do E and F. Okay. So here's E, F, and G. If you're like, man, I really love this stuff, go ahead and do E, F, and G. And I can tell you on G, you're going to want to distribute. On G, what you're going to want to do is you want to use this A minus B over C shenanigans is A over C minus B over C shenanigans. Trust me, that's how you're going to want to do G. Forgot to record. So looking at E, if we have U is the cosine, du is equal to negative sine theta d theta. So that means this just becomes the negative, because I adjust for the negative, 1 over u du. And I end up with a final answer for E of negative the natural log of cosine theta plus C. And on F, u is the sine x, so du is cosine x dx. So I have e to the u du. So this is e to the u plus c, or e raised to the sine x plus c. And then on G, we go ahead and we use the rule that says a minus b over c is a over c minus b over c. So I'm going to distribute that x cosine x underneath each one of those two terms in the numerator. My cosine x cancels on the first grouping, and my x's cancel on the second grouping. So what I really have right now is just 1 over x minus the sine x cosine x. Now we know what, when we see sine x over cosine x, then when we see sine x over cosine x, we know it's going to be the natural log of the absolute value of cosine. And then we have to see if we have to adjust for a negative. And in this case, we don't have to adjust for a negative. And simply doing the integration of 1 over x is going to be the natural log of absolute value of x. And because this has the negative, which E did not, and I'm not going to get the minus the natural log of cosine absolute value. It's going to be positive the natural log of the absolute value of cosine x plus c. And there we have it. And as my husband who is British, he'd say, and Bob's your uncle. I don't know what that means, but he'll say that to me sometime. I'm like, no, he's not. I don't have an uncle named Bob, but whatever. Does anyone have any questions for me on these? Anything at all? The question is, why is it that when I have sine x over cosine x, why does it become the natural log of the cosine, absolute value of the cosine? So I'm going to just go back up here to this one, and I had the sine x, or sine theta over cosine theta. And typically, like I said before, is I like to use the denominator as my u. So I'm going to let u equal my denominator. My my du then is going to be negative sine theta d theta. So this becomes u. Let me do this in blue. This becomes u, and this part here becomes a negative du. And so this integral becomes a negative. I'm just going to pull a negative out. 1 over u du. And so when I do the derivative, or the antiderivative of 1 over u, this is simply just going to be negative the natural log of the absolute value of u plus c, which is going to be the negative the natural log of u, which was cosine theta, plus c. So whenever I see tangent theta or tangent x, then I know that I can replace that with the natural log of cosine, absolute value of cosine x. But I have to make sure I adjust for any kind of negative. If I'm missing the negative, well, on g I had the negative, so I know it's going to be the positive of it. Anything else I can help you with? All right, I want you all to enjoy the weather. We're supposed to get up into the low 70s today. I do have office hour today between 12:30 and 2. Please come in and join me if you have questions. And I have from 10 to 10:50 every day. I have the availability to do one-on-one. You can make an appointment with me. I am kind of full today and tomorrow at 10 to 10:50, but I do have office hour today. And of course, if you need to meet one-on-one at other times, you can just shoot me an email and let me know when you would like to meet, and I'll see if that works into my schedule. Otherwise, you all have a great afternoon and enjoy your 70-degree weather today.